Hello students, we have come to the last segment of our electrochemistry lecture. So this is the third lecture series. If you have missed the first two lecture series, please look at the link located below so that you will be able to go through them before coming to section 5. Okay, so for the final series, we are looking at the last few sections of the lecture notes. Okay, so we'll begin with section 5 on electrolytic cell, which most of you are familiar with from secondary school. This is essentially electrolysis, and maybe to bring you down memory lane, we have a battery here. So for the battery, the longer line represents the positive terminal. The shorter line represents the negative terminal. So the electrodes that is connected to the positive terminal will take on the positive charge, and the electrodes which is connected to the negative terminal will have the negative polarity or the negative charge. Okay, so these two metals are the electrodes. Do take note that the flow of electrons goes from the anodes to the cathodes, and there is no flow of electrons in the electrolytes. Do remember that, because some students have the misconceptions that electrons go through the electrolytes. This is incorrect. Yeah, but in a nutshell, right, the electrolyte needs to be a solution which allows electrical conductivity. So for example, your electrolyte must contain mobile ions. So the example we gave you here is molten lead bromide or aqueous copper sulfate. Because for molten lead bromide, it contains molten lead-2 cations, and bromide anion, which are freely mobile, so they can move, and then they will get discharged at the relevant electrodes, where electrons are being taken up and then move around the circuits. And then for the aqueous copper sulfate, it contains mobile copper-2 and sulfate anion, as well as a small amount of H plus and OH minus, which has been ionized by water, but that's just a very small amount. Yeah, so this is a very important idea which you need to take note of for electrochem. Okay, so again, let me repeat. The electrons do not go through the electrolyte. Okay, the electrolyte merely acts as a medium where the relevant species gets discharged, and in that case, it allows electrons to be pushed through the circuit. Okay, so we have a table here which compares some features of an electrochemical and an electrolytic cell. Okay, so we will first take a look at the electrochemical cell on the left. You should be quite familiar with this because we have been talking about this in the first few segments in the electrochemistry lectures. Okay, so for electrochemical cell, the cell itself, the setup itself is the battery. Okay, so it does not need an external power supply because the setup itself is able to allow a spontaneous reaction to take place. Okay, so in our case here, zinc is being oxidized, and because zinc is being oxidized and electrons is being pushed from the zinc anodes to the copper cathodes, that explains why the zinc anode will take on a negative charge, and then the copper cathode will take on a positive polarity. Okay, and because zinc is being oxidized, the zinc anodes will be electron rich, and copper-2 gets reduced at the copper cathodes, and therefore the copper cathode will be electron deficient. Yeah, and zinc being the more reactive metal, it allows electrons to be pushed from zinc to copper, and this is a spontaneous process. So this is an example of a galvanic cell. Okay, there isn't really a need for you to memorize the polarity of the electrode, because if you solely analyze the processes that is taking place, I think you would be able to come out with the polarity. And do take note that there is a need for you to draw in the salt bridge. And the reason why we need the salt bridge has already been explained in the earlier lectures. Okay, and the voltmeter in most cases is required here in order to measure the potential difference. Okay, yeah. And moving on to the right hand side, we have the electrolytic cell. Okay, so for the electrolytic cell, we are using an external power supply, in this case provided by the battery, to drive an otherwise non-spontaneous process. So in this case, we are driving the electrolysis of dilute sodium chloride solution. Okay, then in our case here, again, the electrons is being pushed from the anodes to the cathodes. And the only difference between an electrochemical and electrolytic cell is that the polarity of the electrodes are different. Okay, so for electrolytic cell, the anode is positive, whereas the cathode is negative. That can easily be explained as well. Yeah, because for an electrolytic cell, as what I think we discussed earlier on, the key thing to remember about what happened at each electrode is not so much as to remembering their polarity, but it's to remember the process that's taking place. So for the cathodes, reduction is taking place. For the anodes, oxidation is taking place. Yeah, so in the case of our electrolytic cell here, at the anodes, oxidation is taking place, and at the cathode, reduction is taking place. So in this case, the positive electrodes is able to attract the anions or species related, so that oxidation can be taken place. And when oxidation takes place, electrons is being lost to the anode, and in this case it is being driven around the circuits. Okay, and the negatively charged cathode will then be able to attract the relevant species, including cations, allowing reduction to take place. Okay, so if you really need to remember, just remember that the polarity of the electrodes for electrolytic cell depends on the terminal in which the electrode is being connected to. Yeah, so that is very important. And for electrochemical cell, it is dependent on what exactly is happening at that particular half cell. Okay, all these mnemonics, I don't think I want to go into details because I don't really like to use all this as well. But if you find them useful, you may use them. Okay, and most importantly, you need to recognize that for the flow of the circuits, it goes from the anodes to the cathodes. That is important. Okay, yeah, I think this is mentioned over here. Polarity of the electrodes are reversed, but again, there isn't a need to memorize. What is important is to basically understand what exactly is happening. Okay, I think it is nicely summarized in this particular paragraph over here. So electrolytic cell, I need an external power supply to drive the otherwise non-spontaneous process, and that is why electrons are being supplied to the cathodes, and electrons are being removed from the anodes, or being driven away from the anodes by the external power supply. Okay, so with that, we'll move on to section 6 on predicting the products of electrolysis, and that is in line with one of the learning objectives. Okay, so electrolytic cell cathode is negative, so cations are attracted. I think it's sort of mentioned earlier on, and then they are reduced. Anode is positive, attracts anions, so anode is to the anodes, and they are therefore being oxidized. Okay, but do take note that it is not always anions and cations. That could be molecular species that could be nearby as well, and depending on the we need to look at the reduction potential values to decide which is being oxidized or discharged, or which is being reduced. Okay, yeah, then I think it's mentioned in the next paragraph over here. So that's something which you can highlight. When there's more than one species, the substance that is liberated is the one which requires the least energy, and the selective discharge, either oxidation or reduction, you can look at it by comparing the E values, which we are going to showcase to you later on. Okay, and then for 6.1, electrolysis of pure molten salts, this is pretty much similar to what you have learned in secondary school or during your O-level or IP days. Okay, so if we have molten lead bromides, in our case here, the inert electrodes, the cathodes will attract lead 2+, okay, and the anodes will attract bromide. And for the case of the cathodes, we'll be able to get, depending on the temperature, so lead will be deposited, or you'll find lead, liquid lead floating around the electrode. And then for the anodes, liquid bromine will be produced, but if the temperature is too high, then you probably will get gaseous bromine. Yeah. Do take note that when you write down the equations, you have to write down the actual process that is taking place. So for cathodes, reduction is taking place. So the state symbols is very important because it's molten. So make sure that you have lead 2+ molten plus 2 electron, and in the process you get liquid lead. Okay, and for the anodes, liquid bromide anion is being oxidized to gaseous bromine. Okay, so do take note of this, and the temperature again is quite important. So the melting point of lead bromide is about 373 degrees Celsius. Yeah, so therefore I would expect bromine to be vaporized and lead to remain as molten. Okay, yeah, so do remember the single arrow, because in the past some of your senior wrote in equilibrium arrow, and you'll be marked down during assessment. Right, okay, so next we'll first look at exercise 6.1 when you are required to predict the product form at the anodes, okay, and the cathodes when liquid magnesium chloride is electrolyzed using inert electrodes. Explain your reasoning, write equations including state symbols for the electrode reactions. Okay, so you are given the melting point of magnesium chloride, which is 714 degrees Celsius. Melting point of magnesium is 650 degrees Celsius. Okay, because I have molten magnesium chloride, so therefore what is going to happen at the cathodes, okay, will be liquid magnesium cations will receive electrons, okay, and it will be reduced to magnesium. Okay, and since we are given the melting points, I would expect magnesium to remain in the liquid state. Okay, and then at the anodes, what happens is that I would expect the chlorides, okay, the liquid chloride to lose electrons to produce chlorine gas. Okay, chlorine is likely to be a gas. Of course, it has to be a gas because it's a gas even at room temperature. So at about over 700 degrees Celsius, obviously it's a gas. Okay, and in the process, 2 electrons is being given away. Okay, yeah. So do take note that when electrolysis takes place, that means that when you apply an external power supply, or an external power supply is being applied to the system, you expect migration of the cations to the cathodes and the anions to the anode. The reason being you are using an external power supply to drive the reaction. Yeah, so the otherwise non-spontaneous reaction will be driven, and that explains why the relevant species will migrate to the relevant electrodes. Okay, next we'll look at 6.2, electrolysis of dilute aqueous solutions. Yeah, so aqueous salt solutions, mixtures of ions and water, and so we have to compare the electrode potentials of the ions and water to predict the products at each electrode. Okay, so again, without going further, this is not very different from what you learned in secondary school. Yeah, but what I want to stress to every one of you with regards to the difference from what you learned in secondary school is that if I'm not wrong, in secondary school, you indicate that the H plus ions migrates to the cathodes and the OH minus anion migrates to the anodes. Okay, if I'm not wrong, this would be the representation in secondary school. However, this is incorrect. Okay, please take note of this. Yeah, so maybe I should write it down so that you will remember for life. Okay, so please do not write things like H plus migrates to cathodes and OH minus migrates to anodes. I do believe this is what was presented to you in secondary school. Do take note that this is absolutely incorrect. Why is that the case? I think from acid-base equilibrium, we understand that this is definitely not the case. Yeah, because molecular water is in large excess. The concentration of H plus and OH minus are very, very low. Okay, so therefore, because of the external power supply, we are able to potentially reduce water at the cathodes, and potentially we are able to oxidize water at the anodes. Do remember this. Yeah, so please remove away this segment of H plus to the cathode, OH minus to the anode from your memory from secondary school. Yeah, the earlier you are able to remove this for your memory, the better it is. Okay, then in that case, is it then wrong to say that OH minus will never be discharged at the anodes? No, it can. I mean, if you are using sodium hydroxide aqueous, of course you can get OH minus being discharged, or if you are using molten magnesium hydroxide, that is definitely possible. Okay, so do remember that. Okay, so let us move on to aqueous sodium chloride solution, electrolysis using platinum electrodes. Okay, so what we're going to do now is we are going to look at two reduction potential values. You can get these values from data booklets, but for simplicity, we have just presented to you in our lecture notes so that you don't have to flip over to your data booklet to check them out. Okay, so at the cathodes, there are two potential reaction or two potential reduction that can take place. Okay, the first is the reduction of sodium plus aqueous to sodium. The next one is the reduction of water to H2 and OH minus. Okay, so if you copy in the reduction potential values, that will be minus 2.71 volts and then minus 0.83 volts. You'll notice that the reduction of water to H2 has a more positive reduction potential as compared to that of sodium plus to sodium. And because of that, the reduction of water will preferentially occur. Okay, yeah, so the basic thing is how you want to go about deciding is to write down the half equation at the cathodes side by side and then compare them and look at which is more positive. Okay, and the more positive one will be preferentially occurring at the relevant electrodes. Okay, so therefore when we are writing down the reaction at the cathodes, this is the reaction which we'll be writing. H2O being reduced to H2 and OH minus. Okay, and sometimes you don't even need the data booklet to help you. Why is that the case? Because I think all of us are aware that when we dumped in sodium metal in water, it will be a very explosive reaction. Yeah, so if you are aware of that, then the production of metal in aqueous medium is therefore not possible. So because of that, I think none of us will predict that sodium plus will be preferentially discharged at the cathodes. Okay, at the anodes is a little bit tricky. Okay, so a little bit tricky. So we have to check this out. Okay, so at the anodes, again, we will write them down as the reduction potential. Okay, so chlorine chloride, that's positive 1.36 volts. Oxygen water, so that's positive 1.23 volts. The first thing I want all of you to take note of is that the two values are quite similar. Okay, the two values are quite similar. Yeah, so because the two values are similar, it is possible to use concentration term, right, to drive one over the other. Okay, meaning that if I have concentrated chloride solution, the position of equilibrium will lie more to the left, and therefore the reduction potential value will become less than 1.36 volts. So potentially it can drop below 1.23 volts, and different things can happen. Okay, yep. Anyway, I've jump start a little bit, so pardon me for that. Okay, so but do remember this: we are looking at an oxidation process, and these are reduction potential values. Yeah. So therefore, right, what we want to look at is we want to choose a reduction potential that is less positive. Okay, less positive. Yeah. Because the less positive the reduction potential is, the more likely will be the species on the right being oxidized, or the greater will be the tendency of the species on the right to be oxidized. Yeah. So therefore, in our case here, because the reduction potential for oxygen/water is less positive than that of chlorine/chloride, water will be oxidized at the anodes. Okay. So the reaction at the anodes will therefore be the oxidation of water to give us oxygen gas and H+. And this is the overall reaction. Okay, and I do believe all of you remember that in secondary school, you are aware that if we are using concentrated sodium chloride solution, or what we call brine, chloride will be preferentially oxidized at the anodes. Yes. And that is exactly what I have mentioned earlier on, but I think I've jump started it. Okay, so maybe I can just discuss it over here. Yeah, so imagine this. If I have concentrated chloride solution, okay, so let's say I have very concentrated sodium chloride solution. Okay, I expect the POE, the position of equilibrium of let's say 1 to shift left. Okay, so therefore I expect the reduction potential value for chlorine chloride to be less positive than 1.36 volts. And because the reduction potential for chlorine chloride is very near that of oxygen water, it is highly possible that the value can be dropped below that of oxygen water by using concentration alone. So let's say I use a very concentrated solution of chloride, it might even be lesser than 1.23 volts. So much so that it becomes less positive than oxygen/water, and therefore chloride will be preferentially oxidized at the anodes. Okay, yep. So we are probably going to discuss that later. Okay, so I just jumpstart a little bit so that I hope I do not confuse you. Okay, so the above is effectively the electrolysis of water. So pure water is not used. Yeah, so therefore, if we want to perform electrolysis of water, we might need to ensure that the water is able to conduct or it has mobile ions. Yeah, so free mobile ions. So we'll usually add in some sodium chloride or even some dilute acid. Okay, yeah. So we'll first be looking at exercise 6.2. Okay, we are required to predict the products formed at the anodes and at the cathodes when the following liquids, okay, so the keyword here is liquids, are electrolyzed using inert electrodes. Okay, inert electrodes means that the electrodes are not being oxidized or reduced at the respective electrodes. Okay, so we have sodium bromide aqueous. Okay, so for sodium bromide aqueous, I think we will not discuss too much for sodium plus, because the idea for sodium plus is similar to that for aqueous sodium chloride solution. Okay, yeah, so I don't think I will want to flip back to the data booklet to discuss much. So what I'm going to do over here is basically just to indicate that at the cathodes, okay, I expect water, okay, to be reduced to give us hydrogen gas, and OH minus. Okay, yep. The bromide is the one which I thought we want to discuss a little bit. Okay, so I'll just go straight to the data booklets. Okay, yeah. So unlike chlorides, where the reduction potential is 1.36 volts, the reduction potential for bromides is 1.07 volts. Yeah, if you compare that to oxygen water, which is 1.23 volts, you will notice that bromine-bromide reduction potential is less positive than that of oxygen water. Yeah, so because of that, I would expect under the condition, under the set condition, bromides will be preferentially oxidized to give us bromines. Okay, yeah. So for a proper working, I think you need to write down the half equations for bromine bromides as well as oxygen water, like how we did over here. But because of the lack of space, I will not be writing it down. So please write it down on your own, and then write it down on your own, and then write the reduction potential value next to it, and then conclude that because the bromine bromide reduction potential is less positive than that of oxygen water, so bromide is preferentially oxidized at the anodes. Okay, so therefore in this case at the anodes, I expect bromides to be oxidized to give us bromine aqueous plus 2 electrons. Okay, yeah. And then next we'll look at aqueous copper 2 fluorides. Okay, yeah. So we're going to go through the same thought process. Okay, so for copper 2 fluorides, again, we are going to look at this particular half cell. Okay, so it's copper 2 copper, so that's 0.34 volts. Okay, and then we are also going to look at the reduction of H2O. Okay, yeah, I think it's over here. Yeah, so the reduction of H2O to give us H2. So that's minus 0.83 volts. Yeah, so did you notice that the copper 2 copper reduction potential is more positive than water H2 reduction potential? Yeah, so if you notice that, that means that at the cathodes, okay, so at the cathodes, I would expect copper 2 aqueous to be preferentially reduced to give me solid copper. Okay, yeah. And then what about at the anodes? Okay, so what's going to happen at the anodes? So again, I'm just going to shift to look at the anode. So for the anode, we have fluorine fluoride, which is a whopping 2.87 volts. So fluorine is a very powerful oxidizing agent. So to oxidize fluoride is a near impossible task. Okay, then it'll be the same thing here. Oxygen H2O. Okay, over here. So this is the oxygen H2O. That's 1.23 volts. Yeah, so for oxygen H2O, it is less positive than that of fluorine fluoride, which is a whopping 2.87 volts. Yeah, so because of that, similarly, similar to the sodium chloride example we have here, what's going to happen at the anode will be the oxidation of water to give us oxygen gas. Okay, so I'm just going to write it down. So H2O liquids will be oxidized to give us oxygen gas plus 4H plus 4 electrons. Okay, yeah. So again, my apologies that I'm not able to write down the two half equations for us to compare it like the way we have it here because of space constraint. But I think exercise 6.2 is straightforward enough for you to understand the thought process that is going on. Okay, so there isn't a need for us to write them down for discussion. Alright. Then next we'll be discussing exercise 6.3, which is on the electrolysis of aqueous sodium sulfate. Okay, so it contains a litmus indicator. So it carried out in the apparatus shown below. So it's something like a U-tube. Okay, inert electrodes are used. Okay, so likely to be platinum. After some time, volumes of gas liberated were as shown in the diagram. Okay, litmus at both compartments has changed color. Okay, so we are supposed to write the appropriate ion-electron half equation. This is another way of asking you to write down the half equations. So sometimes they call it ion-electron half equations with state symbols for the changes which takes place at each electrode compartments, indicate whether oxidation or reduction has occurred. Okay, so again, as all of us have understood from earlier example, sodium sulfate is basically just used as an electrolyte. Okay, so what is happening at the negative and positive electrodes is simply the oxidation and reduction of water. Okay, very similar to the examples we have for the electrolysis of aqueous sodium chloride. Okay, so because of that, I will simply just write down the answer straight away. So at the negative electrodes is when reduction takes place. So H2O will be reduced to give us hydrogen gas. Okay, and 2OH minus. Okay, and this is where reduction took place. And at the positive electrode, H2O is being oxidized to give us oxygen gas, 4H plus and 4 electrons. Okay, and this is where oxidation takes place. Okay, so as the reaction proceeds, I expect the negative electrode to become increasingly more alkaline and the positive electrodes to become increasingly more acidic. Yeah, so because of that, I expect the color of litmus at the negative electrode will be blue, and that at the positive electrodes will be red. Okay, and for B, hence explain why the volumes are in the ratio of 2:1. Okay, I think from the electron transfer you are able to tell. Yeah, because for every 1 equivalent of hydrogen gas that's produced, 2 electrons is required for the reduction. Yeah, but for every 1 equivalent of oxygen being produced, 4 electrons accompanied. Yeah, so in that case, oxygen to the oxygen to hydrogen ratio will forever be 1:2. Yeah, because remember that we are using an external power supply to drive the reaction. Yeah, so therefore the electrons on both ends must balance. Yeah, so if I supply 4 electrons to the positive electrodes, in this case to the anodes, I must take in 4 electrons from the cathodes. Okay, so therefore the ratio will always be 1:2. Okay. Yeah. Another way you can look at it simply by just adding the two half equation up and then balance the equation. Yeah, but that is not. I mean, you don't get a very good conceptual understanding for this. Yeah. So a better conceptual understanding is to understand that as the battery, right? Whatever electrons I give to the cathodes, I must balance it by abstracting the same amount of electrons from the anodes. Okay, yeah. And then I think I've answered part C, state and explain the color of the litmus around the electrodes. Okay, I think earlier on I mentioned that because the cathodes becomes increasingly more alkaline, I expect the litmus to turn blue, and the anodes become increasingly more acidic. I expect the electrode the litmus to turn red. Right. Okay. Then next we are at section 6.3. Okay. Electrolysis of concentrated aqueous solution. I think earlier on I have unknowingly explained this. Okay, so if you like to, you can just read through them on your own. Okay, it has got to do with the shifting of the position of equilibrium. I think I've explained this as well. Yeah, so basically, if I have a high concentration of chloride, I expect the position of equilibrium of 1 to lie to the left, and because of that, the forward reduction reaction is not as favorable. So the reduction potential value will drop below 1.36 volts. And with a very high concentration of chloride, it is likely to drop below 1.23 volts. And because of that, chloride is preferentially oxidized at the anode. As to the exact concentration, it's not required for your curriculum. Okay, because that probably requires some calculations. Yeah, so not to worry, when it's required, then we'll give you the relevant information for you to perform the calculation. Okay, yeah, so in our case here, chloride is correct. Chloride will be preferentially oxidized at the anode to give us chlorine gas instead of water being oxidized to give us oxygen. Okay, at the cathode is the same thing. Water will be reduced to give us hydrogen gas. Yeah, as I mentioned, the reduction potential between sodium plus sodium and water H2 is too different, too far away. And we all know from common knowledge that sodium is highly reactive, so it will immediately react with water if I put a piece of sodium in water. Yeah, so we will never predict sodium being produced in an aqueous medium. Okay, next we have background information on overvoltage. You can read on your own or consult me during tutorials. Okay, I think it's some interesting facts which you can usually read more beyond your curriculum. Yeah, basically, if we want to produce oxygen and hydrogen via electrolysis, usually it will require a greater voltage than it is predicted by the standard electrode potential. Yeah, so we say that H2 and O2 needs an overvoltage before they are discharged. Yeah, and this is usually needed because of the high activation barrier. Yeah, but sometimes because of this, we might end up producing undesirable products. Okay, yeah, and sometimes in the question we might ask you why is undesirable products, or why are some of the undesirable products being formed. Okay, then next we have section 6.4, electrolysis using active electrodes. Yeah, so we understand from secondary school, because we learned that platinum and graphite are chemically inert. Okay, yeah, but sometimes the electrode themselves can undergo oxidations at the anodes, so this is known as an active or reactive electrodes. Yeah. Do take note that although graphite is inert, sometimes it will react with the oxygen produced to give us carbon dioxide and carbon monoxide gas at high temperature. Okay, so in the electrolysis of copper sulfates using copper anodes, it is possible that at the anodes end, copper will be oxidized to give us copper 2. Yeah, because if you compare with all the few reduction potential values being given to us, the copper 2 copper is the least positive amongst all. So because of that, copper is preferentially oxidized at the anodes. Yeah, so when you're using the copper electrodes, the copper anodes will dissolve and copper 2 will enter the solution. Okay, yeah. But if we perform electrolysis of copper sulfate using platinum electrodes, then again, similar story to that of what we have seen earlier on. Water would be preferentially oxidized at the anodes. Right. Okay, so now we have exercise 6.4. Predicts the reaction that occurs at each electrodes when the following aqueous solutions are electrolyzed using platinum electrodes. Okay, so do take note, platinum electrodes. Okay, so dilute sodium hydroxide. So again, same story. At the cathodes, you know that sodium plus will not be reduced. Yeah, so therefore we are writing the same thing. So 2H2O liquids. Oh, sorry, not liquid. Liquids. Plus 2 electrons. I will get H2 gas plus 2 OH minus. Okay, aqueous. And then what happens at the anodes? Yeah, so at the anodes, because now I have OH minus. Okay, so I would expect OH minus to be oxidized to oxygens and H2O, okay, plus 4 electrons. Okay, and some of you might be wondering why did we choose this particular equation instead of the one we have earlier on involving water. Okay, yeah, so I'm just going to show you. You will notice that the one involving water, right? Okay, so let me just erase this. So I'm just going to highlight. Okay, so in an alkaline medium, OH minus, I expect it to be preferentially discharged. Okay, so we have basically we need to compare water being oxidized or OH minus being oxidized. Yeah, but the half equation, or the reduction potential of oxygen / OH minus is less positive than that of oxygen / H2O. So because of that, I'm going to choose this equation when OH minus is directly oxidized to oxygen gas. Okay, which is what I've chosen here. Okay, so next, we are using dilute sulfuric acids. Okay, so at the cathode, so again, dilute sulfuric acids, water versus H plus. Okay, so of course, if you look at the data booklets, the reduction of water is more negative than that of the reduction of H plus over here. Okay, so I expect the equation at the cathode to be H plus. Okay, so H plus will be reduced to give us hydrogen gas. Okay, and then at the anode, again, it's the same story. I expect water to be reduced. Okay, same story as what we discussed earlier on. Okay, so oxygen plus 4H plus plus 4 electrons. Okay, aqueous. Okay, so next, what about silver nitrates? Okay, so silver nitrate, again, we are going to compare between water, the reduction of water, which is negative 0.83 volts, versus the reduction of silver. So reduction of silver is much more positive. So I expect silver to be reduced at the cathodes. Okay, so silver will be reduced at the cathodes to give us solid silver. Okay, then what about at the anodes? Okay, so for the anodes, nitrates, the nitrate is already in its highest possible oxidation states. So I will not expect nitrate to be further oxidized. So yep, we're going to follow what we have earlier on. So I'm going to expect water to be oxidized to give us oxygen, and H plus, aqueous, and 4 electrons. Okay, so what about a solution of calcium chloride in dilute nitric acid? Yeah, so over here we have a few species to look at. We have H plus. I think we are familiar with H plus. Yeah, H plus reduction potential is 0. And then we have calcium to calcium, which obviously is not likely to take place. It's very negative. Okay, and we have water. Okay, so water to H2 again is negative 0.83 volts. Yep, so that's not going to work. Yeah, so what is likely to happen will be the reduction of H plus to give us hydrogen gas. Okay, yeah. Then at the anodes, again, anode could be a little bit more challenging because here we have nitrates, we have chlorides, and then we have H2O as well. Yeah, so again, I think earlier on we have already briefly mentioned nitrate is not likely to take place because oxidation of nitrate is already the nitrogen in nitrate is already in its highest possible oxidation state. Yeah, so if you want to oxidize it further, that's almost impossible. Chloride is possible, but we're looking at probably at a dilute solution. Yeah, so again, I expect water to be oxidized. Okay, so same story. Water will be oxidized to give us oxygen and 4H plus and 4 electrons. Okay, yep. And then finally, we have part B, predict the reaction that occurs at each electrodes when dilute H2SO4 is electrolyzed using a platinum cathode and brass anodes. Okay, so equations for the cathodes. Yeah, so again, at the cathodes, we expect reduction to take place because we have dilute H2SO4. So at the cathodes, I expect again is a competition between H2O and H+. And earlier on, we have already seen that the reduction potential for H plus H2 is more positive than that for H2O H2. Yeah, so therefore at the anodes, I expect 2H plus to be reduced to give us hydrogen gas. Okay, then what about at the anodes? Okay, so at the anodes, we have active electrodes. Yeah, so between copper and zinc, zinc is more likely to be oxidized as compared to copper. Yeah, the reason is because zinc to zinc has a less positive reduction potential as compared to copper to copper. Yeah, so because of that, I expect zinc solids to be reduced, to be oxidized into the solution as zinc 2 plus aqueous. Okay, plus 2 electrons. Okay, then some of you might be wondering, why is it that I am only comparing between zinc and copper? Why not? Why can't we look at whether water can be oxidized? Well, we can do that. Okay. If you want to look at water being oxidized, you can look at the H2O. You can look at the relevant half equations. Okay. I think this is the one we are looking at. Yeah. So, do you think zinc to zinc is less positive than oxygen water? Zinc to zinc, remember, is negative 0.76 volts. That's obviously less positive than that of oxygen water. Yeah. So, when you compare across the three categories, zinc to zinc, which is negative 0.76 volts, copper to copper, which is positive 0.34 volts, oxygen water, which is positive 1.23 volts. So obviously zinc will be oxidized to zinc 2 plus aqueous. Okay, yeah. So I hope you are clear about what is going on. Next, we'll be looking at section 7 on calculations in electrolysis. Okay, if you read the first line, the amount of substance produced during electrolysis is directly proportional to the amount of electrons that's passed through the cell. This is quite important. I think you can understand this from the balanced redox half equation. So for example, in the electrolysis of molten lead bromides, which we have seen in section 6.1, if we have 2 electrons being passed through the cell for the cathodes, you will notice that 1 mole of lead-2 is being reduced to 1 mole of lead, and then at the anodes, 2 moles of bromide is being oxidized to 1 mole of bromine, and in the process 2 moles of electrons is being accompanied. Okay, so this is exactly what we meant when we are trying to say that the moles of the amount of substance is proportional to the amount of electron being transferred in the process or passed through the cell. Okay, and we're going to introduce to something a little bit more physics. Over here, 1 mole of electrons carries a charge equivalent to a Faraday constant. The Faraday constant can be found from your data booklets. It's actually the second constant in section 1. The value given is 9.65 times 10 to the power of 4 coulomb per mole of electrons. So that is the charge carried by 1 mole of electrons. Yeah. If you want to stretch this a little further, right? Basically 1 mole of electrons contains the Avogadro constant, Avogadro number of electrons. So therefore, right, that will be 6.02 times 10 to the power of 23 electrons in 1 mole. Okay, then each mole or rather each electrons will carry a charge of 1.60 times 10 to the power minus 19 coulomb. So if you multiply the Avogadro number by the electronic charge per electrons, that will be 1.60 times 10 to the power minus 19. You should end up with a number very close to the Faraday constant. Yeah, but you will not get exactly 96500. You'll get around like 9648 something or 96447 something. Okay, yeah, that's because we have done a number of approximation here, like, you know, the Avogadro constant is not exactly 6.02 times 10 to the power 23. It's actually 6.023. Okay, and then of course the Faraday constant, we round it up. Yeah, but if you are a little bit confused by what I just said, actually it doesn't really matter, because the important constant is in your data booklets. So you just need to know where to find the necessary values. Yeah, so that will be 96500. Okay. Yeah, and of course the quantity of charge then, that is the total charge being carried, right, is obviously the total number of electrons, or the number of most electrons multiplied by the Faraday constant, and is given by this particular equation. Okay, then the amount of substance produced at each electrode, as we have found earlier on, right, is directly proportional to the quantity of charge. Okay, so that will mean that we will need to equate it to the factor which will affect the quantity of charge. Yeah, so based on physics, or based on principle already derived earlier on, you probably need to know that the quantity of charge is equals to the current multiplied by the time. The time should be in seconds. So the units is very important. So the current is in amperes and the time is in seconds. Okay, so if you you understand that these two relationship has quantity of charge as the subject. So if you equate these two up, you will get current multiplied by time equals to the number of moles of electron transferred multiplied by Faraday. Yeah, so you notice that this is one of the most important relationship you need to know for H2 Chem, especially when you want to perform electrolysis calculations. Yeah, so if you are able to derive or work out this particular relationship, it will help you a lot in your calculation. Okay, yeah. And then of course the last paragraph is pretty important. You will notice that the amount of substance produced is only dependent on the currents, or you can say that it's the magnitude of the current and the duration of the current being passed. Yeah, so it does not depend on the concentration of the ions in the system. Yeah, I think this is very important, because quite often MCQ question will catch you unaware. Okay, yeah, so just be careful about this. Yeah, we'll look at some exercises. Okay, so in particular 7.1, 7.2, 7.3, and then based on the exercises, I think you will learn how to apply the equations we have just talked about above. Okay, so for exercise 7.1, you are required to calculate the quantity of charge in coulombs. Okay, of course it's in coulombs, because in most cases, at least for the H2 level, we are only using coulombs as the units. Okay, so calculate the quantity of charge required to liberate 44.8 dm³ of chlorine at standard temperature and pressure in the electrolysis of molten sodium chloride using inert electrodes. Okay, if you forget about your STP condition, you can just go back to the data booklets. You can shift down a little bit. Okay, so under STP condition, the molar volume is 22.7 dm³. Okay, so from here, I think the first thing we need to do is to calculate the number of moles of chlorine produced. Okay, so we can simply just put down the number of moles of chlorine is therefore equals to 44.8 divided by 22.7. Okay, and based on you can refer to the data booklet if you want, or you can just work it out based on fundamentals. Yep, so you know that in order to produce 1 mole of chlorine, okay, I need 2 moles of chloride, Okay, and in the process, 2 electrons is being transferred. Okay, yeah. So because of this, we need to equate or we need to find the stoichiometric ratio between chlorine and the number of moles of electron transferred. Okay, so therefore the ratio will be 1:2. Yeah, so therefore from here, the number of moles of electrons transferred, okay, the number of moles of electron transferred will therefore be equals to 44.8 divided by 22.7 multiplied by 2. Okay, if you punch your calculator, you should end up with 3.95 moles. Yeah, and if you recall what we have earlier on, because we are required to calculate the quantity of charge, yeah, so therefore Q is equals to the number of moles of electron transferred multiplied by Faraday. Yeah, so Faraday, please use the value given in your data booklets and not any other value. So it's 96500. Yeah, so that will be equals to 3.95 multiplied by 96500. Okay, so you should be able to get 3.81 times 10 to the power of 5 coulombs. Okay, yeah. Then next we'll move on to exercise 7.2. A technician needs to plate a bathroom fixture with 0.86 grams of chromium from an electrolytic bath containing chromium sulfates. Okay, yeah. If he is expected to complete the job in 10 minutes, what would be the minimum current required? So assuming the electroplating process is 100% efficient. Okay, so yeah, so the first thing we need to do obviously is we need to go to the data booklet, because if we are given values in mass, it's not very helpful because we need to convert them to amounts or number of moles. Yeah, and over here, my electrolytic bath contains chromium 3 sulfates. Yeah, so we need to base it on what we understand. So from chromium 3 sulfate, that's chromium 3 plus. Okay, it needs to take in 3 electrons in order for it to be reduced to chromium. Yeah, so the stoichiometric relationship between chromium 3 and electrons will be 1:3. Okay, yeah, so from here, you can very easily calculate the number of moles of electron transferred. Okay, simply by just taking 0.86 divide by the relative atomic mass. Okay, so we just go to the all the way to the end. That will be the periodic table. So that's 52.0 for chromium. Okay, so that's divided by 52.0, and then remember the ratio is 1:3, right? So multiply by 3. Okay, so if we punch our calculator, we should be able to get 0.0496 moles. Okay, and because the technician is expected to complete the job in 10 minutes, and then I need to calculate the minimum current. Yeah, so therefore what I'm going to do now is I need to equate Q to IT, and of course at the same time we also need to equate the IT to the number of moles of electron transferred multiplied by Faraday. Okay, yep, and then I will need to calculate the minimum current required. So therefore from here, the minimum current required will be I equals to number of moles of electron transfer will be 0.0496. Okay, and then I'm going to multiply by 96500, and then I'm going to divide by the time. Okay, so the time is in minutes, so we need to convert that to seconds, so that will be 10 multiplied by 60. Okay, so if we punch the calculator, we should get around 7.98 amperes. Okay, so I hope you find the application pretty straightforward. Okay, so next we'll move on to exercise 7.3. Okay, so over here we have a current of 0.025 amperes is passed through a solution of sulfuric acids, okay, for 4 hours. So again, we have the time in hours, so we need to do some conversions using inert electrodes. So write equations for the electrode reactions and calculate the volume of gas formed at each electrode at room temperature and pressure. Okay, I think from earlier examples, I think under section 6 we should be able to quite easily discuss what happens at the cathode and anodes, okay, if you recall from what we did earlier on. Okay, so at the cathodes, I would expect H plus to be reduced to give me hydrogen gas. Okay, and then at the anodes, I will expect water to be oxidized to give me oxygen, and then this is accompanied by 4H plus as well as 4 electrons. Okay, yeah. Remember that the electrons taken in and produced is a little bit different, so eventually their ratio needs to be similar. So we'll find a way to work that out very soon. Okay, but first please bear this in mind. Okay, I think the first thing we need to do is because we are given currents, we are given a time, right? So we need to calculate the quantity of charge transferred. So that will be the currents, which is 0.025 multiplied by the time. Yeah, however, the time is given to us in hours, so we need to convert to seconds, so that will be 4 hours. So 1 hour, that's 60 minutes multiplied by 60, and then 1 minute 60 seconds multiplied by 60 again. So with that, I'm going to get 360 coulombs. Okay, and of course we know that Q is equals to the number of moles of electron transferred multiplied by Faraday. Alright, so therefore the number of moles of electron transferred is equals to the quantity of charge, that's 360, divided by the Faraday constant, that's 96,500. Okay, then we punch our calculator, we should be able to get 3.73 times 10 to the power of minus 3 moles over here. Yeah, and this quantity of electron transfer must be the same for both the cathode and anode. Yeah, please remember this, because if you don't remember this, you will not be able to perform any kind of reasonable calculation. Okay, yeah, then from here we'll be able to calculate the number of moles of H2 produced, so that will be half of 3.73 times 10 to the power of minus 3 moles. Okay, then therefore the volume of hydrogen produced will be this number. Okay, 3.73 times 10 to the power of minus 3 multiplied by 24. If you forget, I can just shift back to the section 1, so you can take a look. Just give me a while. Section 1, yeah, so section 1 we have RTP, 24 dm cube, 1 mole of gas will occupy 24 dm cube. Okay, so I'll just multiply 24, and then it will be equals to 0.0448 dm cube. You can convert it to cubic centimeters, so that will be 44.8 cubic centimeters. Okay, and then for the oxygen produced, yeah, so again it's the same thing. The number of moles of oxygen will be equals to a quarter of 3.73 times 10 to the power minus 3, and then therefore the volume of oxygen will be this whole chunk here multiplied by 24. Okay, so yeah, so that will be half of 44.8, so I'm going to get 22.4 cubic centimeters. I just convert it straight away so that you do not need to go through the thing and get 0.0224 dm3 and then convert to cubic centimeters. Yeah, because I can just follow the ratio I have above. Remember that the volume of oxygen produced is always half that of the volume of hydrogen. Okay, next we'll look at exercise 7.4. So we have an electric current passed through solutions of copper 2 sulfates, silver nitrates, and dilute sulfuric acid. Yeah, so this is a little bit complicated. We have 3 cells over here. So the first cell contains copper sulfates. Okay, so that's, I'm going to highlight in blue. Okay, because it's copper sulfates. Okay, going to highlight in blue. So this is the first cell, and then after that, the next cell I have silver nitrate, and then this is followed by sulfuric acid. Okay, and then we have a variable resistor here. Okay, and then the easiest way is to assign the polarity at the respective electrodes. Okay, so we have a direct current negative terminal here and positive terminal over here. So therefore the electrodes directly connected to a negative terminal will be the negative electrodes. Okay, and then if this is negative, so the other electrode will be positive. Okay, and then the electrode connected to the positive terminal will take on the positive charge, and therefore you will have the positive polarity. And then we continue with this, so the next one will be minus, and then plus and minus. Yeah, just make sure that the plus minus are alternate, because if it doesn't alternate, then something is wrong lah. Yeah, your cell will not work. If you don't understand why, please think about it. Okay, yeah. And then of course the next thing is to look at the processes that is taking place at the respective electrodes lah. Yeah, so this is an electrolytic cell. Okay, so what happened at the negative electrodes over here, that will be the electrodes where reduction takes place. Yeah, because the negative electrodes will attract cations. Okay, so because reduction took place, so this will be the cathodes. Okay, this will be the cathodes, and then of course it will be followed by anodes, and then of course over here will be anodes, cathodes, anodes, cathodes. Okay, so I won't go into details. Try to figure out on your own. Okay, and then of course the respective products is given to us. So the products at the cathodes in cell 1 will be copper. Okay, I don't think it comes as a surprise because the reduction potential of copper 2 to copper is more positive than that involving involving water. Okay, yeah. Then let's look at the question. So it's connected in series for 20 minutes. We are using inert electrodes, so therefore the electrodes are not taking part in the reaction or in the electrolysis. So if 0.21 grams of copper is deposited in the first cell, calculate the mass of silver deposited in the second cell. Notice that you are not given the current. Yeah, so because you are not given the current, then therefore it's utmost importance for you to calculate the number of moles of electron transfer, because that should be the same for all the cells. Okay, yeah, so therefore we'll try to do a simple calculation first. So because I have 0.21 grams of copper deposited in the first cell, yeah, and based on what I understand, the equation involving copper is copper 2 plus 2 electrons, and then I'm going to get copper. Yeah, so the number of moles of electrons transferred to the number of moles of copper is 2:1. Okay, so therefore the number of moles of electron transferred is therefore equals to 0.21, and then the relative atomic mass of copper is 63.5, and then I'll need to multiply by 2. Okay, and if I punch my calculator, I should be able to get 6.61 times 10 to the power minus 3 moles. Okay, yep, so that will be the first cell. Okay, then for the second cell, right, if we want to calculate the number of moles of silver deposited, that was being asked by the question, mass of silver deposited in the second cell. Okay, so we need to look at the number of moles of electron transfer, okay, for 1 mole of silver to be deposited. So Ag, silver is silver 1, and then plus electrons, I'm going to get silver. Okay, remember that the number of moles of electron transferred must be the same. Yeah, so therefore the number of moles of silver deposited will be the same as the number of moles of electron transfer in our case here, because it's 1:1 ratio. So that will be 6.61 times 10 to the power minus 3 moles. Okay, so therefore the mass of silver deposited will be 6.61 times 10 to the power minus 3 multiplied by the relative atomic mass of silver. That will be 107.9. Okay, so we take the calculator, we punch in the numbers, we should be able to get 0.714 grams. Okay, so that will be the answer to part A. And then for part B, the volume of hydrogen liberated at room temperature and pressure in the third cell. Okay, so that's over here. Okay, so what we can calculate would be, again, the number of moles of electron transfer must be the same. Yeah, so for the third cell to liberate hydrogen gas, we need to write a balance equation for the cathodes. So that will be 2H plus 2 electrons, and then I'm going to get 1 equivalent of hydrogen gas. Yeah, so therefore the ratio of electrons to hydrogen is 2:1. Okay, so from here the number of moles of hydrogen produced will be half that of number of moles of electron transfer. So that will be half times 6.61 times 10 to the power minus 3. So I'm going to get 3.31 times 10 to the power minus 3 moles. Okay, so therefore the volume of hydrogen evolved will be this particular number multiply by 24. So I'm going to get 79.4 cubic centimeters. Okay, you can leave it in dm cube. Okay, so not an issue. That will be 0.0794, but it's just that the numbers doesn't look so nice. Okay, and then of course the current passed. That will be pretty straightforward because you know that Q is equals to current multiplied by time. You are aware of the time because you were told that it's 20 minutes. Okay, so therefore the current will be equals to the number of moles, I mean the charge. Okay, so we'll work that out slowly. That's Q over time. Okay, and we know that the total charge transfer is the number of moles of electrons multiplied by Faraday, and that's divided by time. Okay, then the number of moles of electron transferred will be the same as this. Okay, 6.61 times 10 to the power minus 3 multiplied by Faraday constant, that's 96500, multiplied by time, that will be 20 minutes multiplied by 60 seconds. Okay, so if you take out the calculator and punch the values, the current will be 0.532 amperes. Alright, okay, so that's the whole working for exercise 7.4. It's a little bit complicated because of the numerous cell involved. Yeah, but the fundamentals doesn't change. Yeah, so remember that the total number of moles of electron transfer for each cell must be the same. Okay, due to the conservation of charge and conservation of material. Okay, yeah. Then next, we're going to move on to this bit, which I have already shown you earlier on. Yeah, so remember that Faraday is defined as the quantity of charge carried by 1 mole of electrons, right? Yeah, so 1 mole will be 6.02 times 10 to the power 23, and then the charge will be 1.6 times 10 to the power minus 19. Yeah, so Faraday can be derived from this. Yeah, and you will also notice that if you are able to perform the right kind of calculation, you are able to calculate a value of the Avogadro constant in the lab. Okay, if you are able to perform some lab work. Yeah, so that will be quite interesting. Okay, so that will bring us to exercise 7.5, where we were told that a current of 0.5 amperes was passed for 1 hour 40 seconds. Okay, I think from here you can easily determine the quantity of charge transferred. Okay, so I can just do the calculation first. So that will be Q is equals to IT. So the current is 0.50, and then I will multiply it by time. So the time is because 1 hour is 60 minutes, and then each minute 60 seconds, so there will be 60 times 60 plus 40, because there's an additional 40 seconds. Okay, I'll take the calculator and punch. I should get 1820 coulombs, or 1820 coulombs. Okay, and then we were told that the electrolytic cell contains aqueous silver nitrate as the electrolytes and silver as the electrodes. So the electrode is an active electrode. So 2 grams of silver was deposited on one of the electrodes. Yeah, given the AR of silver to be 108, so just use it. No need to use the data booklet 107.8. Yeah, so also 107.9. No need to do that. Okay, and then electronic charge is minus 1.6 times 10 to the power minus 19 coulombs. Minus is due to the fact that electrons are negatively charged. So at which electrode was the silver deposited? What is the polarity? I think this would be straightforward, because depositing silver will involve reduction, because silver plus, okay, so silver plus in the aqueous medium will take on an electrons from the electrodes, and you'll get reduced to silver. Okay, yeah, so that will be the cathodes. Okay, so this will be the cathodes because reduction is taking place, and then the polarity of the electrodes will be negative. Yeah, this is in order to attract the positively charged cations. Okay, and then calculate the quantity of charge in coulombs. So I've calculated it to be 1820 coulombs. And then finally, B part 2, using only the data provided and your answer to B1, calculate a value of the Avogadro constant. Yeah, so that should be relatively straightforward. Okay, because the first thing we need to do is to calculate the number of moles of electron transferred. Yeah, so that will be equals to the number of moles of silver deposited. So I'm not only number of moles of silver deposited, but also find out the ratio between the silver deposited and the number of moles of electron transferred. So in this case, it happens to be 1:1. Okay, so therefore in this case, I'm just going to sub in 2.0 divide by the AR, which is 108. Okay, because in the question we were told is 108, so we need to put in 108, and then multiply by 1. Okay, you need not want to multiply by 1, but if you want to do that, you could. Okay, not sure whether it is 108 or 107.9 in your notes, but it doesn't really matter as long as you are on the right track. Okay, and then you should get 0.01852 moles. Okay, yeah, and then you are aware that based on the earlier equation, so the Faraday is equals to L multiplied by the electronic charge, right? Okay, yeah. So therefore from here, what can we do? Yeah, so therefore we can calculate the number of electrons. Okay, so number of electrons, just give me a while, the stylus is not really working. Okay, so that will be equals to 0.01852 multiplied by L. So L is the Avogadro number. Okay, so remember that L is the Avogadro number. Okay, and we know that Q is equals to the number of moles of electron transfer multiplied by Faraday, which is equals to number of moles of electron transfer multiplied by L multiplied by the electronic charge. Okay, so I just put it as E. Okay, yeah, so and we know that the total charge transfer is 1820, so that will be 1820 equals to the number of moles of electrons, so that will be 0.01852, and then multiplied by L multiplied by the electronic charge, which is 1.60 times 10 to the power minus 19. Okay, and then if we do a quick calculation, let us try to perform a calculation and see what numbers we'll end up with. Okay, just give me a while. 10 to the power of 19. Okay, and then let's see what I will get. Multiply by this. Okay, and then yep, so I will end up with 6.143 times 10 to the power of 23. Okay, yeah, so you can leave it as 3SF. That will be 6.14 times 10 to the power of 23. Okay, so this will be the answer, which is a value for the Avogadro number. Okay, yep, so with that, we'll move on to the next part, which is on planning. Yeah, so remember, this is the planning icon. Okay, so if to construct an electrolytic cell and determine a value of the Avogadro constant or the Faraday constant. Yeah, so again, the approach will be to set up an electrolytic cell using external power supply. Okay, usually a 5-volt direct current battery and an ammeter. So the ammeter is to measure the current. Okay, the value of the current, and then you also need a stopwatch in order to measure the time. And then of course you need to ensure that the polarity of the electrodes is correct. Remember earlier on, this is minus and plus. The longer one is plus, the shorter one is minus. Okay, and then the generic procedure, I think you can just read through it here. Okay, so this is an example of to set up for the electrolysis of copper sulfate, where copper is being deposited in one of the electrodes, and then for the other electrodes, copper will be oxidized. And then for figure 20 over here, right, you have electrolysis of water. Yeah, and then in the process, you are going to measure, or in this case, measure the volume of oxygen being produced. Okay, yeah. So normally for the generic procedure, right, do remember to use sandpaper to remove the oxide layer. Okay, and then of course there's a need for you to wash the anode with water and then with ethanol, and then dry it and weigh it accurately. Why do we want to use the anodes? Okay, because the anode will be oxidized, right? So you're going to measure the change in the mass. Okay, yeah. So so over here, right, you will notice that my anode is one whole piece of metal, and then after some of the metal is being oxidized to the cation, it will then diffuse to the cathodes. Some of you might be thinking, actually cathode is okay as well, right? Because at the cathode, right, the metal will be reduced. Yeah, but sometimes it's difficult because the reduced metal, right, might not stick very firmly to the metal surface, so some of it might fall off. Yeah, so using the anode is often a better choice. And then I think earlier on I mentioned some of the key things, like you need a stopwatch. Okay, remember to close the circuit. Okay, and then you need a stopwatch. You need to measure the currents, you need to measure the final time, and then of course the final current reading. Yeah, because over time the current will fluctuate, so you probably need to take an average. And then after that, determine the mass lost for the anodes. Just take the difference. Yeah, but of course before you take the difference, make sure that you need to dry your anodes and reweigh it, because you don't want to weigh it with the water present. Okay, and then of course the mass loss, right, you can easily convert to number of moles, and then from the number of moles you can convert to the number of moles of electron transfer. Okay, so that's where you can obtain the coulombs. The quantity of charge in coulombs. And then from there you apply what we learned earlier on, like quantity of charge is number of moles electron transfer multiplied by Faraday, and then Faraday is Avogadro number multiplied by the electronic charge. Yeah, and then from here you can perform your the necessary calculation. Okay, and then of course if you wish to, you can also measure the volume of the gas produced. Yeah, but usually measuring volume of gas produced can be, or via gas collection, may not be as accurate because some of the gases may escape. Okay, if you wish to, sometimes you can also perform a titration on the electrolytes. If for example the product enters the electrolytes. Okay, but just an example. So let's say for example iodide is being oxidized to iodine. So technically you can titrate the amount of iodine present by pipetting out a fixed volume of iodine, and then you titrate it with thiosulfate, and then later on you scale to the total volume. But remember that before you do that, you need to stir to ensure that the iodine or the electrolyte is well dispersed, is homogeneous, is a homogeneous solution. Okay, so what are the sources of errors? So it could be high measurement error due to small change in mass, high percentage error in that sense. Okay, then or it can be due to the fluctuation in the currents. Yeah, you may begin with, let's say, 9 amperes, but even at the end of the day you may end up with, say, 7 amperes. So it could add on to the uncertainty. Okay, and then you can also suggest what you want to do to limit or eradicate the error. So for example, use a longer time so that I have a greater mass loss. Okay, and that will give us a smaller percentage error or a variable resistor. Okay, so I think earlier on I mentioned about the variable resistor. It looks something like this. If you're not familiar with physics, you can ask your physics friend, but yeah. So something like this is like a variable resistor. Okay, so if you have a variable resistor, you can kind of try to fix the current or try to ensure that the current is a constant throughout the duration of the experiments. Okay, so by and large, that will be the planning which we will introduce to you on how to write a generic procedure. Of course, it is question dependent, so you have to exercise some flexibility when you're working through the problems. Okay, yeah. Then with that, we'll move on to the final section, which is section 8 on the applications of electrolysis. Okay, so this part on the application of electrolysis, we will focus on the electrolytic purification of copper. It shouldn't come as something which is very new to most of you. Perhaps later on when we use the standard reduction potential values to help us understand a little bit more about the purification, perhaps that is the part that is new to most of you. If not, then I guess the bulk of it you have already learned them in secondary school. Okay, so we probably understand that the abstraction of copper is very important, and in this case, when we want to purify copper, we will perform what we call electrolysis. So we will usually connect the impure copper to the anodes. That's because anodes is when oxidation takes place. Yeah, so the impure copper will be oxidized to copper 2, and then itself will be reduced over at the cathodes. So usually at the cathodes, we'll put a pure piece of copper, yeah, so as not to contaminate the reduced copper from copper 2. Okay, yeah. So normally what happens at the impure copper anode is that there are two things that are likely to happen. Yeah, so first of all, any metal less reactive than copper, right, will not be oxidized alongside copper. So in that sense, after some of the copper has been oxidized, right, those metals such as silver and gold, because they are not as reactive as copper, so they will actually fall off as what we call the anode sludge. The reason why we call that a sludge is because it appears like a bit sluggish and some bits and pieces of solid. Yeah, and it's usually not very useful unless we can gather them together and then maybe melt them again and then perform another round of electrolysis to extract out whatever metal that is present. Yeah, then any metal that is more reactive than copper will then be oxidized alongside copper. Yeah, and then you'll be thinking, if they are more reactive than copper, they will be oxidized together with copper to the relevant cation. But both the oxidized form of the more reactive metal as well as copper 2 will then migrate to the cathodes. Then you'll be thinking, wouldn't both of them be reduced at the same time? No. If you look at the reduction potential values, right, any metal that is more reactive than copper, they will have a smaller tendency to be reduced because they will have a more negative reduction potential. Yeah, so because of that, only copper 2 will be reduced at the cathodes. Yeah, so that is the general basis of electrolysis when we want to perform it on for the purpose of purifying copper. Okay, and we also need to take note that our electrolyte is a solution of copper 2 sulfate. Yeah, I mean, obviously we need copper 2, then we don't want any other metals to contaminate the solution. Okay, so yeah, I think over here I have already mentioned the bulk of what was being written here. So we have anode, which is the impure copper, and then the cathode, the pure copper. Okay, and then I think I've gone through some of these ideas, so you can read them on your own. Okay, and then we'll need to check out which is preferentially reduced. Yeah, so any metal more reactive than copper will not be preferentially reduced. So only copper 2 will be reduced. Yeah, and in that case, we'll get a purified sample of copper. Yep. So there's a net transfer of copper from the impure copper anode to the cathode in that sense. Okay, so that is something which is a resultant of the electrolysis, because remember the number of moles of electrons are transferred on both sides must balance lah. Yeah. However, right, if my impure copper contains metal more reactive than copper, then of course some of the copper 2 will actually come from the copper 2 sulfates. Okay, yeah, then the more reactive metal will then remain in the solution as the cation ion floating around. Okay, yeah, I think if we use an example, it might be clearer. So we'll have exercise 8.1 over here. So this is on the electrolytic purification of copper. Yeah, and I think we'll just jump straight to the question with reference to the reduction potential data. Okay, explain in details the electrode reaction that takes place during this electrolysis. Okay, and explain how each of the two impurity metals, so zinc and silver, is removed from copper. Okay, yeah. So I think what is important now is to look at the data booklets. Okay, so again we have silver and zinc, so we need to write down the reduction potential values. Okay, so silver plus silver is positive 0.80 volts, so I'm going to write it down over here. So silver plus aqueous plus electrons, silver solids. Okay, so this is plus 0.80 volts. Okay, and of course we have copper to copper, which is over here, so that's 0.34 volts. Okay, so copper to aqueous plus 2 electrons. Okay, copper solid, so this is 0.34 volts. And then we have zinc, which is right at the end. So zinc to zinc is negative 0.76 volts. So zinc aqueous, okay, so this is negative 0.76 volts. Okay, yeah. Okay, so right now we are aware of the setup, right? The setup is exactly like this. Okay, yeah. So we need to make some decision what's going to happen. Okay, so therefore, right, if we apply a potential difference such that copper can be oxidized to copper 2, then we expect any metal with reduction potential more positive than copper to copper will not be oxidized. Yeah, so in this case here, right, the silver will fall off as the anode sludge. Okay, so we need to be very clear about that, because we are supposed to explain how each of these impurity metal is being removed. Yeah, so the silver will fall off as anode sludge. The reason being because the reduction potential of silver plus silver is more positive than that of copper to copper. Yeah, I think you have to mention this explicitly. Okay, and then at the same time, almost at the same instance, right, zinc will be oxidized to zinc 2 plus. Okay, so what happens at the anodes is that solid zinc, right, will be oxidized to zinc 2 plus aqueous in the solution. Okay, of course, at the same time, at the anode, right, copper will also be oxidized to copper 2 and plus 2 electron. Yeah, so if copper can be oxidized, any metal more reactive than copper will also be oxidized. This is no choice. Okay, why is that the case? Because the reduction potential of zinc to zinc is more negative than that of copper to copper. Yeah, so any metal more reactive than copper will also be oxidized, so no choice. Yeah, so these are the two reactions that is taking place at the anodes. Okay, and then what about at the cathodes? Okay, so at the cathode, right, we have to compare the reduction potential values. So at the cathode, right, you notice that copper to copper is more positive as compared to that of zinc to zinc. Yeah, So therefore, right, at the cathodes, only copper 2 will be reduced to solid copper. Yeah, because the reduction potential of zinc 2 zinc is more negative, or you can say less positive than copper 2 copper. Yeah, zinc 2 is not being reduced, and it will remain in the solution as the aqueous cation. Okay, so remember this. If the potential difference, or if the voltage in the battery being applied, right, is sufficient to oxidize copper to copper 2, it will also be sufficient to oxidize zinc to zinc 2. Yeah, but I must apply my potential difference such that silver is not being oxidized. Because if silver is being oxidized, we are asking for trouble, and you will add into a complication, because silver plus will then, or there will be a chance for silver plus to be reduced at the cathodes, and then my copper is not exactly being purified in the process. Okay, so do remember some of these things whenever you are performing electrolysis. Of course, for the H2 curriculum, we will not be very explicit about asking you what do you think is a voltage you need to apply, because that requires some industrial chemical engineering knowledge and some optimization to be done. Yeah, but at the back of your mind, you need to be aware that I must apply the voltage large enough for copper to be oxidized, but not for silver to be oxidized. Okay, then another process we need to be aware of. So the first one is the electrolytic purification of copper. Then the second one will be the anodizing of aluminium. Okay, so basically aluminium is a reactive metal that can be oxidized easily. Yeah, but we want the aluminium object to have a fairly constant in thickness layers of aluminum oxide. Yeah, so the process of getting this particular surface treatment, this particular coating, is known as anodizing of aluminium. Okay, and in the process, right, we want to ensure that the thickness of the aluminum oxide sort of increases, so that it will make the aluminium more resistant to further corrosion, or to be resistant for any form of corrosion, to the best of our ability. Okay, so in this case, we will put the aluminium over at the anodes, because we want oxidation to be taking place at the surface of aluminium, so that in the process, aluminium will be oxidized to aluminium 3+, and then due to the complex mixture, or the complex series of chemistry involving water in the system, therefore aluminum oxide will be formed at the surface of the aluminum anodes. Yeah, then over at the platinum, over at the cathode, we will use an inner electrode. Okay, so therefore electrolyte is dilute sulfuric acids. We have aluminum objects to be anodized, and then cathode will be either platinum or graphite. Okay, there is nothing wrong with this. Please take note of this. Sulfuric acid is correct. You might be thinking that, wouldn't sulfuric acid react with aluminium? Actually, yes and no, because why is that the case? Because remember that on the surface of aluminium, right, there is a aluminium oxide layer. Yeah, so this aluminium oxide layer being formed, right, is so resistant to corrosion such that in the presence of dilute acid, it will not react so readily, unless you remove that aluminum oxide layer. Yeah, so for simplicity, right, and in order to sort of be consistent with what we have or what we learn about in industrial chemistry, right, the reaction happening at the anode, right, this is one of the representation which we'll accept at the H2 level. So aluminum and water combine. In the process, I will be able to get aluminum oxide and 6H+, and then 6 electrons will be transferred in the process. Okay, and then at the cathodes, hydrogen gas will be produced. Okay, yeah, so do not be so worried about the H+ being produced to react with Al2O3 and then result in the thinning. Yeah, so the process will equilibrate on its own, and it will find its sweet spots. And remember that aluminum oxide is quite a tough layer, so in dilute acid condition, it is not so prone to reaction or corrosion. Okay, yeah, so I think some of it is explained over here, so I think you can read about it. Okay, yeah. So we'll just move on. Okay, I think over here they mentioned that because of the porous layer, it's actually quite easy for it to for dye to stick onto it or intercalate between the layers, so you can get different colors. Okay. Next we'll move on to exercise 8.2. Okay, it's another process which is not exactly directly in your syllabus, but you can use your knowledge to apply and work on the question. I think in secondary school you have worked on something like this before. Okay, so this is to manufacture sodium hydroxide and sodium chlorate once via electrolysis of brine. So it's a modified question from the past A level, okay, in 2005. So the diagram below shows the diaphragm cell used for electrolysis of concentrated sodium chloride, which is known as brine. This is commercially important industrial process, okay, used to make chlorine gas, hydrogen gas, and aqueous sodium hydroxide. Yeah, so you notice that this kind of setup, usually it will be built very near to the sea, so that you can get seawater easily. Okay, so that is brine, concentrated sodium chloride. Okay, so what's going to happen here is that concentrated sodium chloride will be introduced over here. Okay, and then we will have graphite or titanium anodes. Yeah, and as what we have seen in the earlier section of this chapter, for concentrated sodium chloride solution, chloride will be preferentially oxidized instead of water. Yeah, so in this case, chlorine will be produced. And because chlorine is being produced as a gas, so it will be found over here, and then it will be driven off. Yeah. And then on the other hand, at the cathodes, I'm going to expect OH minus to be reduced to hydrogen gas. Okay, in that sense. Yeah. Okay, and then we'll look at the question first. Okay, so for part A, oh sorry, I think I mentioned something incorrectly. It's not OH minus, but it's actually water. So water will be reduced to hydrogen gas, and in the process OH minus will be produced, and the sodium plus that was remaining earlier on, right, will combine to give us sodium hydroxide, which can be emptied off over here. So overall we have three products: hydrogen gas, chlorine gas, and sodium hydroxide. Okay, so with reference to the reduction potential data, right, explain why electrolysis of dilute sodium chloride produces mainly oxygen gas at the anodes, whereas electrolysis of concentrated sodium chloride solution produces mainly chlorine gas. Yeah, we have already covered this in the earlier section. I think it should be section 6.3. So if you are interested, you can go and review the answer again. But very quickly, I will just jump straight into the data booklets. Okay, if you look at the reduction potential value of chlorine chloride, that is 1.36 volts. Okay, and then the reduction potential values for water and just give me a while. Where is that value? Okay, oxygen water is 1.23 volts. You realize that the two values are quite similar. I mean, not very similar, but yeah, they differ by about 0.1 volts apart. Yeah, so if I'm going to use concentrated sodium chloride solution, I would expect the position of equilibrium to shift to the left. So when the position of equilibrium shift to the left, right, the reduction potential value will become less positive. Okay, and because the difference between the reduction potential value of chlorine chloride is about 0.1 volts or 0.13 volts to be exact, away from that of oxygen water, right? Yeah, it is possible for the reduction potential to drop below that of oxygen water. Yeah, so when that happens, then chloride will be preferentially oxidized in the anodes. Okay, so I think the answers has already been summarized earlier on as well. But I thought I'd just run you through the process, remind you again. And then for part B, the sodium hydroxide made in the diaphragm cell is formed in aqueous solution that suggests with the aid of appropriate half equation how sodium hydroxide is obtained. Yeah, so as mentioned earlier on, over at the cathode, the sodium will not be reduced. Yeah, because it has a very, very negative reduction potential. Yeah. However, right, the reduction of H2O over here. So the reduction of H2 actually produces hydrogen gas and OH minus. Yeah, so the hydrogen gas will be found here. Okay, and then the OH minus, right, together with Na plus, yeah, it will form a solution of sodium hydroxide. So again, that can be used for that can be stored and used for other purposes, or it can be sold off as an important chemicals, because sodium hydroxide, of course, is a very important chemicals used in almost everyday lab. Okay, yeah. And then for part C, in the diaphragm cell, the anode is made of titanium and the cathode is made of steel. Why steel is never used for the anodes? Okay, I think first of all we need to understand what does steel contains lah. Okay, so steel actually contains iron. Okay, so if iron is used as the anode, right, you expect iron to be oxidized instead of chloride. The reason why you expect iron to be oxidized, right? Again, let's look at the reduction potential value. So I expect iron to be oxidized to iron 2 because iron 2 iron reduction potential is actually less positive than that of chlorine chloride. Yeah, so because of that, I would expect iron to be oxidized to iron 2. So steel cannot be used in the anode. If not, it will dissolve. Yeah. And of course, we can answer the question from another angle as well. The chlorine gas produced will also corrode the steel because it can react with iron to give us iron 2. Yeah, so therefore, we should never use steel as the anode in the electrolysis of brine. Okay. And then for part D, right, the asbestos diagram prevents a negative ion produced in the cathode compartment from moving into the anode compartment because the negative ion may be oxidized in preference over Cl minus. Use the data booklet, right, equation to show how this negative ion may be oxidized. Again, the negative ion, I think it's quite clear from here, is OH minus. Okay, so from the data booklets, let us try to find one involving OH minus. So I think this is the one. Yeah. So OH minus can be oxidized to oxygen gas and water, and in the process 4 electrons is being accompanied. Okay, so we can write that in over here. So 4 OH minus equals will be oxidized to oxygen gas plus 2 H2O and then plus 4 electrons. Explain why this negative ion may be more readily oxidized than chloride. Yeah, so again, we look at the reduction potential values. Okay, so the reduction potential value of oxygen OH minus is 0.40 volts, whereas that of chlorine chloride is 1.36 volts. So it is actually less positive, and the difference in the reduction potential value is large. Yeah, so therefore, I would expect it to be more readily oxidized than chloride. Okay, yeah, then the second last part, suggest one large scale use for each of the products. Yeah, so I think that's pretty straightforward. Chlorine can be used as a swimming pool disinfectant, or it can be used in bleaching. Okay, and of course, I think the title here suggests in the manufacture of sodium chlorate 1. Okay, which is largely bleach. Okay, and then cathodes, hydrogen gas, can be used to produce ammonia in the Haber process with nitrogen. Okay, or you can use it for catalytic hydrogenation of unsaturated oil. Okay, yep. Sodium hydroxide. Sodium hydroxide, I'm sure it has been explained to you earlier on as well. So sodium hydroxide, I can use it as a common benchtop chemicals. Okay, and of course there are a lot of uses for sodium hydroxide, including synthesis, because in the synthesis we saw a lot of reagents such as ethanolic KOH. Finally, part F, the asbestos diaphragm is removed and the content of the cell are stirred so that chlorine reacts with sodium hydroxide to form sodium chloride and the bleach. The cell is kept cold. Construct a balanced equation for the disproportionation reaction. So this is a revision of redox. It must be kept cold because if it's warm, right, sodium hydroxide and chlorine, right, it will cause chlorine to disproportionate to a higher oxidation state, which is plus 5. That's chlorate 5. Okay, yeah. So again, it's a bit of down memory lane on what we did in JC1. So a simple way to write balance equation, of course, in our case here, is simply just to write it as chlorine. Okay, and then to give us chloride -1, and chlorate +1. Okay, so you notice that it's just nice because 0. So one of the chlorine gets oxidized, gets reduced to -1. Okay, so it will take 1 electron, and then the other chlorine will give out the 1 electron. So give 1 electron. Okay, so imagine that these two chlorine, one chlorine give the other chlorine 1 electron. So it will be oxidized and the other chlorine will be reduced. Yeah, so the ratio is correct. It's 1:1:1. Okay, and then now the only thing we need to do now is to balance the charge. So the total charge on the right hand side, if you look at the charge here, is -2. So we need 2 OH minus to help us balance. Okay, and of course water, as what I mentioned in JC1 last year, it will be balanced miraculously. Okay, so in this case plus H2O. Okay, because the question wrote sodium hydroxide, sodium chloride, and sodium chlorate, right? If you wish to, you can also include the spectator ions. So therefore the balance equation would be NaOH, 2 equivalent of it, plus Cl2, and in the process I get sodium chloride plus sodium chlorate 1, okay, plus H2O. Okay, so I hope that is fine with everyone. Right, okay, and then the final exercise, which is 8.3, we have electroplating. Okay, so for electroplating over here, it's a relatively novel scenario. So we have an aqueous solution containing this particular complex, silver 1 complex, with 2 cyanide anion. Okay, so this particular complex is used. This is a very stable complex and produces a very low concentration of silver plus aqueous. Okay, so this is the equilibrium being established. So write an equation including state symbols for the cathodes reaction. So of course, at the cathode reaction, basically I would just expect silver aqueous, okay, to be reduced to silver. Okay, so explain why a very low concentration of silver plus is used. In most cases, right, we want the plating to be done in a thin and uniform manner, and of course in order to do that, I cannot have too high a concentration of silver plus, because if not, then the silver plus will just randomly be reduced on the surface of the object, and then I will get uneven layer of silver. So in general, because we want the deposit to be uniform and at relatively slow rates, which is concentration dependent as well, so we'll use a very low concentration of silver plus. Okay, and then for part B, in order to replace the worn silver coating on a trophy, it is estimated that about 0.5 grams of silver needs to be electroplated onto it. Calculate the length of time that a current of 0.2 amperes has to be passed through the electrolysis bath in order to achieve this. So again, this was what we have. What we learned in section 7 on electrolysis. Okay, so we're just going to apply the equation directly. So first of all, we have 0.5 grams of silver. Yeah, so again, we know that silver plus and silver, and as well as silver solid, is 1:1 in terms of stoichiometric relationship. So therefore, the number of moles of electron transferred is therefore equals to 0.50 divided by 107.9. Okay, multiplied by 1. Okay, so that will be 4.63 times 10 to the power of -3 moles. So again, we'll use Q is equals to IT, okay, and which is equals to the number of moles of electron transfer multiplied by Faraday. Okay, and because the current is 0.2, that's multiplied by T. Now moles of electrons is 4.63 times 10 to the power of -3 multiplied by Faraday, that's 96500. Okay, so if we bring the current down, then we'll get time is equals to 2,234 seconds. Or if you prefer minutes, then that will be equals to about 37 minutes. Okay, so please perform the calculation and check if you are able to obtain this. Yeah, so usually calculation in electrochem is quite straightforward. Yeah, so in general, I do not see students having problems with that. But students usually have problems with the more conceptual question in trying to explain or to be able to tell which species is being oxidized or reduced. So just take note of that. Okay, so moving ahead, we'll be looking at two of our most important topics, which is on periodicity. Those are the last two topics. Okay, so it's on periodicity and transition metal. Then you will notice that in transition metal, we'll be using a lot of reduction potential values as well. Yeah, so that will be the end of the lecture on electrochem. I hope you do not find it too difficult or too dry. Okay, I guess you will need more practice. So please go ahead and work on your tutorial questions before you come back to the lectures on the remaining two topics. Okay, so with that, I thank you very much for listening.